Hello and welcome to this brief presentation on centroids, also termed centres of area. In this presentation we're going to evaluate the centroids of such sections as this shown here, where the centroid location from the base will be somewhere in this region, which we will denote as Ybar from our given datum. To evaluate the Ybar and later on the Xbar of a particular section, we use a tabular method similar to that shown in the sketch. First of all, let's review some basic definitions. Areas. An area may be defined as a quantity of a two-dimensional space that a body or a shape occupies. For complex shapes, an area can be broken down into a number of smaller areas, sometimes referred to as elements. What you're seeing in this section below is a section through a stiffener of an aircraft component. This element here denotes the skin associated with the section, and these elements here are a breakdown of a Z stiffener which actually has a hole in its centre. This could be a typical problem where we have the datum given, which is the outside of the skin line, and we're trying to evaluate the Ybar dimension, that's the dimension to the centroid of the section, from the datum given. Again, some terminology is defined here. We're probably familiar with the term centre of gravity. That's defined as the point at which the whole mass of the body can be considered to be concentrated or to act. Analogous to the definition of the centre of gravity is that of the centre of area, also known as the centroid. The definition of the centre of area or centroid. The centroid is the point in a shape about which all the area can be considered to act. This is the point about which the area of the surface is equally distributed. So above and below the centroid, the area of the section should be the same, and to the left and the right of the centroid, the area should be the same. For a symmetrical object, the centroid is its centre. For example, the centroid of a circle, a square or rectangle can be located at their respective centres. So the centroid of the circular dartboard shown here would be at its bullseye. Exercise 1, we're asked to locate the centroids of the following shapes. The centroid of the circle is easy to find, we just bisect two diameters. For the square, we bisect the corners to find the centroid. I would encourage you now to stop the presentation for a moment and determine the centroids of the following shapes. If we want to find the centre of the rectangle, again I'm bisecting the corners. Here's the centroid. The centroid of the equilateral triangle is a third up from the base. Because it's symmetrical about the vertical axis, the centroid will be somewhere there. The centroid of this right angled triangle will be a third the way up from the base and a third the way in from the left hand edge, so it will be somewhere in this region here. The centroid of this symmetrical eye section would be in its middle, somewhere here. The centroid of the unsymmetrical eye section, where the lower flange is smaller than the upper flange, its centroid might be in this region here. The centroid of the T-section, the centroid location will move closer to the flange, so somewhere in there. And the centroid of the equal L section will actually be in free space, somewhere there. Note wherever the centroidal axes occur, we assume the area above and below are the same. So if we have a centroidal axis through here of this particular section, this means the area above that centroidal axis is equal to the area below the centroidal axis. Taking the T section here, our centroidal axis now is in this region. So again, the area above the centroid location is the same as the area below the centroidal location. It's also true if we consider the vertical symmetry of some sections. The area to the left of the equilateral triangle here would be the same as the area to the right of the equilateral triangle. Centroids of common non-symmetrical 2D sections. There are standard formulas available for us as engineers to use when we're evaluating the centroids of these unsymmetrical sections. On the left hand side here we have the centroid of a right angled triangle given to us. Notice the centroid in the vertical sense is a third of the height given, and the centroid in the horizontal sense is a third of the width given. So that defines the centroid of a right angled triangle in the x and the y sense. And we're also given here the centroid of a semicircle, shown here. And that's defined in the vertical as 4 multiplied by the radius, r in this case, divided by 3 multiplied by pi. And again, these are standard formulae given to us without proof. Exercise 2 wants us to calculate the x bar and the y bar values for the triangle, shown on the left hand side here, if the base is 30 millimeters and the height is 120 millimeters. And the exercise also wants us to calculate the y bar of the semicircle if the diameter given is 1 meter. I'd encourage you to stop the presentation and briefly attempt this exercise. The answers are shown here for the rectangle, 10 millimeters and 40 millimeters, and also the centroid of the semicircle, 0.212 meters. The solutions are shown on the following slide. Exercise 2 solution. For evaluating the centroid of the right angled triangle, shown here in the left hand side of the sketch, we're given a height of 120 millimeters in the question for the triangle, and we're told in the formula that the vertical location to the centroid shown here, is h upon 3. So if the height is 120 millimeters, then the y bar dimension is h divided by 3. So 120 divided by 3 gives us 40 millimeters in the vertical sense. That's from the base of the triangle. We're also told in the question that the base of the triangle is 30 millimeters. So given the base, we know that the centroid is b upon 3 from the vertical edge of the triangle. So our x bar dimension is b divided by 3, that's 30 divided by 3, so 10 millimeters in this particular case. And for the second part of the question, we're told that the semicircle has a diameter of 1 meter. Notice in the formula for the semicircle, the y bar location is defined as 4r divided by 3 pi, so be careful here. We're given a diameter of 1 meter, so the radius in this case will be 0.5 meters. So to evaluate the y bar for the semicircle, it's going to be 4r divided by 3 pi, 4 multiplied by 0.5 divided by 3 multiplied by pi. That evaluates to a y bar location of 0.212 meters from the base of the semicircle here. So that's evaluating the centroid location using standard formulae. And just for reference, below is an extract of centroid information from published sources. Engineers often refer to standard information in textbooks, reference books, etc. And here you can see a triangular area is given where we have the y bar location and the formula for area. We have a quarter of a circle. We have an x bar location, a y bar location, and the area. Here we have a semicircular area where we have a Y-bar location and the area of a semicircular formula. And you can see there's various other shapes that are given here with their locations of their centroids and their areas. As just a reference to indicate that there are standard formulas, standard tables that we often access when requiring to evaluate the centroids of particular sections. Just a brief comparison here between the centre of gravity and centre of area. So centre of gravity. If the mass of an object per unit area is constant, then the centroid of the surface area of the object lies directly over the centre of gravity, as shown in the figure. So here is the centre of gravity within the three-dimensional object, and above it on the surface is the centre of area. So we can see from this illustration that the centre of gravity and the centre of area can be related. But the centre of area relates to a two-dimensional shape and the centre of gravity relates to a three-dimensional object. Now in evaluating the centroids, we're going to use a concept termed the moment of area, sometimes termed the first moment of area because in other analyses there is what's called a second area moment also. So just as we can have the moment of a force, which we've looked at in previous presentations, we can have a moment of an area. So the first moment of area of an element is defined as the area of that element multiplied by its distance from some given datum or reference axis. So the first moment of area has the unit of length cubed, and the length may be the metre or the millimetre in the work we're going to review. So in the SI system, the first moment of area is expressed in terms of metres cubed or millimetres cubed. Here's a brief illustration of the first area moment approach used to evaluate centroids. If we consider the first moment of area about the datum axis given in the sketch below, datum axis shown here, for the three shapes that are outlined, we're going to consider each element or each shape in turn, and we're going to use the following general notation. The element N has an area, AN, and a distance from the datum, YN. So consider element 1, which is a square in the diagram below. It has an area A1 and a distance Y1 from the datum axis. So this is area A1 and this is a distance Y1 from the datum axis. If we consider element number 2, which is a triangle below, then that has area 2, which is distance Y2 from the datum axis. So for the triangles, area 2, and there's distance Y2 from our datum. And element number 3 in our sketch is a circle this time. That has area 3 and distance Y3 from the datum axis. So area 3 for the circle and its distance Y3 from the datum. To evaluate the Y-bar, that's a centroid location in the vertical sense, being shown here diagrammatically, we use this formula. We basically add up, summate, that's what that Greek symbol sigma means there. We add up all the ANs multiplied by the YNs, and we simply divide that by the summation of all the ANs, or the areas. So for our nomenclature, the Y-bar is the distance of the centroid from the specified datum, that will be in metres, and the summation of the ANs will be the total area of the section in metres squared. So from our sketch on the left hand side here, to find the Y-bar, in this particular case we have three area moments to evaluate. We have the A1 Y1, that's added to the A2 Y2, and that's added to A3Y3. So we're adding up, we're summating the 3 area moments for the 3 particular sections in the sketch. We then simply divide that by the summation of the areas, so we add up the A1 with the A2 with the A3. And that evaluates to give us the Y-bar location, the centroid location in the vertical sense from the datum given. So that's the basic approach we're going to apply in evaluating the centroids in the following examples we're going to review. We will of course look for the X-bar location as well in some of the questions. Here's a generic solution procedure for finding the centroids. First step, we need to define the datum or the reference axis. Sometimes we're told in the question which to use, and sometimes we have to decide ourselves. And that's from where all the elements centroids will be measured. Step 2, we have to break the section into small elements, usually rectangular elements or circular elements, as that aids the ease of calculation. We have standard formulas for these type of sections. And we need to number these elements, 1, 2, etc. It's quite arbitrary numbering, but they need to be numbered for ease of reference. Step 3, we need to determine the centroid locations for all the elements with respect to the datum axes we're using. Step 4, we need to calculate the respective areas, the ANs in the table, and the first area moments, the AN/YNs, for all the elements about the datums. It's preferable to use a tabular format as we'll show on the following slides. And the 5th step, we actually calculate the location of the vertical centroid, Y-bar, and you'll see later on the horizontal centroid, X-bar, using our formula derived on the previous slide. Y-bar is equal to the summation of the first area moments of all the elements divided by the summation of the area of all the elements. The following slides show you how to apply this procedure to find the centroids of various sections. So example 1, we have an inverted T-section shown below. So we've got to calculate the location of the centroid, so the Y-bar here, in the vertical sense from the horizontal datum that is specified. So here's a datum for this section, and we've got to evaluate the Y-bar, the distance to the centroid location from this datum. Notice all the dimensions are given in millimeters here. So the first thing we're going to do here is to break our section down into 2 rectangles. I've shown the rectangles here. The flange is in purple and the upstand is in green. They're labelled as element 1 and element 2, but that's arbitrary labelling. So what we're going to use here is what's shown as a tabular approach, a nice structured approach to finding the centroids. We'll apply this to every question. The left-hand column here as the element number n. So we have 2 elements in this particular case to consider. And for each we're going to work out the area. We're going to work out its y dimension from the datum. And we're going to work out its first area moment, which is simply the area times the y. And we do that for both sections. Find the area of the rectangle, its y distance from its centroid to the datum, and then work out the area moment. We will then summate the areas. We will summate the area moments. And then to find the Y-bar dimension from our datum, it's simply the summation of the first area moment from our table divided by the summation of the areas from our table. That evaluates to give us Y-bar. Let's now put some numerical values into the table. So consider element number 1, which is a rectangle. We know the width of the rectangle is 32 millimeters, the depth of the rectangle is 6. So we can evaluate the area. 32 multiplied by 6 is 192 millimeters squared. Look at element number 2, it's another rectangle. We know that the width of this rectangle is 4 millimeters, and we know that the height of the rectangle is 36 millimeters. So we can work out the area of the rectangle. 4 multiplied by 36 is 144. What we do now is summate the area, so 192 millimeters squared added to 144 millimeters squared is 336 millimeters squared. That's our area of our section. Next we're going to evaluate the y dimensions for each of the rectangles from the datum given. Considering element number 1 here, its centroid location, if I bisect the corners, will be in this location here. So the centroid for element number 1 from the datum given would be half of the depth, so half of 6 is 3 millimeters. It becomes a bit more difficult to evaluate the centroid of element 2 from the datum, so a little bit more consideration here. Again, if I bisect the corners of this rectangle, then the centroid of the element 2 would be somewhere in this region here. And because the depth of the element 2, the green rectangle, is shown as 36, then the distance of the centroid of the element 2 from the top of the flange here would be 18 millimeters. But don't forget, we must always measure the y dimensions from the datum given. So in this particular case, the y dimension for element 2 will be 18 millimeters, add the 6 millimeters here, the distance to the datum. So 24 millimeters will be the y dimension for element number 2. I encourage you just to think that through for yourself, but that's one of the problem areas that most students have, is determining the y dimensions from the datum. To fill in the final column and work out the area moments, that's quite straightforward. We simply have to now multiply the area, 192 here for element number 1, by the y dimension, and that gives us a value of 576 millimeters cubed for the area moment. For element number 2, to work out the area moment, it's simply the area of element number 2 multiplied by its y dimension from the datum, and that gives us a value of 3,456. What we do next is summate the first area moment, so 576 add to 3,456 is 4,032. And finally we can work out the y bar. It's simply the summation of the area moments for each of the sections, so that's the 4,032 in this case, and that's divided by the summation of the area, which is 336, shown here, and that evaluates to give us 12 millimeters as the y bar dimension in this particular case from the datum. So our centroid is here, 12 millimeters from the datum at the bottom of the section. Now in example 1b, we're going to calculate the y bar again of the inverted T section, but this time our datum is at the top of the section, not the bottom of the section. So what I encourage you now is to start the presentation and try to evaluate the centroid, the y bar, this time from the top of the section using our tabular approach. The areas for the sections 1 and 2 will be the same as before, but their y dimensions will be different. And that's what I want you to think through. What are the y values for element 1 and element 2 shown in the sketch from the top of the section this time? Once we evaluated the y's, we can then work out the area moments, and from that we can work out the y bar dimension, but this time it will be from the top of the section. I'd encourage you to start the presentation and try and evaluate the y bar. The solution is shown on the following slide. So here's the work solution for example 1b. As stated previously, the areas of the respective sections do not change, but the y dimensions now are different. So in this case, the y dimension for element number 1 to its centroid here can be seen to be 39 millimeters. In other words, it's going to be 36 millimeters here plus half of the 6 millimeters of thickness of element number 1. So 36 add 3 will give us 39 millimeters. The centroid location of element number 2 from the datum at the top of the section will be 18 millimeters. In other words, half of the 36 millimeters depth of section 2. We can then evaluate the first area moments as we did before. It's just simply the area of the element 1 multiplied by the y dimension for element 1, so 7,488. And then for element number 2, the area is 144 millimeters squared multiplied by the 18 millimeters from the top datum, so 2,592 millimeters cubed is the first area moment for element 2. So our area summation as before, 336 millimeters squared, and summating our area moments this time is 10,080. So once again we can work out the y bar. It's simply going to be 10,080 millimeters cubed divided by 336 millimeters squared. That evaluates to 30 millimeters, so the centroid location for the datum at the top of the section here will be 30 millimeters. So that puts the y bar location to here. So what we're showing there, with a depth of 42 millimeters, the centroid location is either 12 millimeters up from the bottom or it's 30 millimeters down from the top. So whether we take our datum at the top of the section or the bottom of the section, we end up with the same centroid location. Question 1, I would encourage you to attempt this question. We've got to determine the y bar location from the datum shown, which is at the bottom of the section here, for this unsymmetrical I section. The answers are given in square brackets and the tabular approach is outlined in the slide. Don't forget we have to work out the y bar once we've populated the table with the appropriate values. So I'd encourage you to stop the presentation and attempt this question now. I suggest you split the unsymmetrical I section down into 3 rectangles. The full work solution is shown on the following slide. Here are my 3 sections I've used. Element number 1 at the top, element number 2 is the web, and element number 3 is the lower flange. Be very careful when evaluating the overall dimensions of each of the elements because of the way the section is actually dimensioned. It can be quite confusing. So looking at my areas for element number 1, my area is 120 millimeters multiplied by 40. The flange width here is 120 millimeters, looking at the geometry, and the thickness is 40 millimeters. So 4,800 millimeters squared for element number 1. Element number 2 is a width of 40 millimeters and a depth of 60 millimeters. So the area of element number 2 is 2,400 millimeters squared. And element number 3 has a length here of 200 millimeters, looking at geometry, 80 plus the 40, and a thickness of 40 millimeters. So that evaluates to 8,000 millimeters squared. We can then summate the 3 elements together to find the total area of the section is 15,200 millimeters squared. Now we've got to work out the y dimensions, and they're from the datum at the bottom of the section. So for element number 1, the y dimension to its centroid location would be up here, of course. That would be 40, add 60, add half of 40, so that's 20. So 40 add 60 add 20 is a value of 120. For element number 2, the centroid location will be somewhere up here, and that will be half of 60, so that's 30, and then add 40 from the datum. So 70 millimeters is the location of the centroid of element number 2 from our datum at the bottom. And finally, for element number 3, the centroid will be halfway up the 40 millimeters here, so that will be 20 millimeters. Now we can work out the first area moments for each of the 3 elements. So there's the area moment column populated for the 3 elements, and I've summated at the bottom the total first area moment of all 3 elements from the datum. So now we have to evaluate the y bar location. So 904,000 for the first area moment divided by 15,200 gives us a value of 59.5 millimeters, and that's to 1 decimal place here. In question 2 here, we're asked to determine both the x bar and the y bar from the respective datums for the 80 mm by 60 by 6 mm rolled steel angle section, denoted RSAs. We're then asked to compare the answers we find with the documented values listed in the extract of BS4 in our notes. We've got to state possible reasons for any discrepancies that might exist. So it's a slightly more complicated problem in that we have to work out the X bar as well as the Y bar. So you'll notice the table here has been extended. Our first four columns are the same as in all the previous examples, but this column here with the xn and the a times the xn is evaluating the first area moment about the vertical axis, so we can find the X bar. So our approach this time would be to populate the table as we did before, but this time we will work out the Y bar from the first area moment about the horizontal axis, and we'll also calculate the X bar from the first area moment about the vertical axis. Notice the datums here. This is the horizontal axis datum and this is the vertical axis datum shown here. I would encourage you to stop the presentation and try and populate the table as far as you can. Working out the areas, the YNs and the AYNs is the same as in the previous slide. We just need to work out now the xn values, the horizontal distances from the vertical datum, and then the a and xn values. You'll obviously need to break the unsymmetrical L section into two rectangles to begin with. If you think you can attempt those final two columns, I would encourage you to do so, but the full work solution will be shown on the following slide. So question 2 solution. Here's my breakdown. I'm going to have the rectangle split this way with element 1 and element 2 shown here. You don't have to break the section down as I've shown, but that's my suggestion. Next we need to work out the areas of the two sections. So from the geometry given, element number 1 here, the area is going to be 6 mm, the 6 mm width here. And that's multiplied by 74 mm, which is the height of element number 1. So this is 74 mm, and we find that by subtracting 6 mm from the 80 mm here. So 80 subtract the 6 gives us 74, and that's the height of the element 1 the way I've depicted it on the sketch here. The area for element number 2 is easily found. It's simply the 60 mm by the 6 mm, so 360 mm squared for the area of element 2. As always, we just add the areas up to find the summation of area, so 804 mm squared. Now we need to evaluate the Y dimensions for each of the sections. For element number 1, the centroid locator element number 1 will be here. And it will be half of the 74 we had on the previous diagram, which is 37. And then we'll add 6 to that from our datum at the bottom. So 37 add 6 is 43 mm. So that's where the 43 mm has been arrived from. There's our 43 mm, the centroid of element number 1. Element number 2, it's much easier to find the centroid from the datum at the bottom, which is half of the 6 depth, so that's where the 3 mm is arrived from. Now we have to evaluate the X dimensions, and these will be dimensions from the vertical axis shown here, which is where the datum is defined, but we're measuring in the horizontal direction. So again, considering the centroid of element number 1 in the horizontal dimension, that will actually be half of 6 mm. It will be 3 mm in from the vertical end here. Now considering the centroid of element number 2, this region here, that will be half of 60 mm from the vertical datum, so that's where the 30 mm is derived. 30 mm in from the left hand end. To evaluate the first area moments is the same procedure as before. And to illustrate how the area moments are calculated as before, to calculate the first area moment about the datum at the bottom of the section, it's simply the area multiplied by the y, produces the first area moment about the datum at the bottom. But this time to find the area moment about the vertical axis, that would be the area multiplied by the x dimension for an element and that will give the AX value, and that's about the vertical datum we're using. We simply summate the AN, YN values to find the first area moment about the datum at the bottom here, and then we summate the AN, XN values to find the first area moment about the vertical datum here. So to find the Y bar, it will be 20,172 divided by the area of 804 millimeters squared. So that's 25.1 millimeters to 1 decimal place. And to determine the X bar, that's 12,132 millimeters cubed divided by the 804 millimeters squared. That gives a value of 15.1 millimeters to 1 decimal place. So there's our solution for the X bar and the Y bar for question 2. Now question 1 wanted us to compare our X bar and Y bar calculated values, shown here for convenience, to those of British Standard 4 specification for hot rolled sections. This is an extract from the standard for unequal angles, which is what we have here. Just notice in the table below that BS4 actually states its properties in centimetres. So for the section we were considering on the previous slide in question 2 was an 80 by 60 by 6 millimetre thick angle section. And what we've got on the table for BS4 is the area of the section and the distance to the centre of gravity, they mean centroids here for us, from the various datums shown here, the vertical datum and the horizontal datum. Also, to add to confusion, the nomenclature is slightly different. Their Y dimension is our X dimension and their X dimension is our Y dimension. So in other words, their X bar is our Y bar and vice versa. So first of all, let's consider the area for this section. For the British Standard, that's 8.11 centimetres squared. Converting that to millimetres squared, that would be 811 millimetres squared. Go back to our table on the previous slide, we actually had 804 millimetres squared for our cross-sectional area. If you now look at their X bar dimension, which is actually our Y bar dimension, they've got 2.47 centimetres, so that's 24.7 millimetres. Our Y bar dimension was 25.1 millimetres. And considering BS4's Y bar dimension, which is our X bar, they have a value of 1.48 centimetres, that's 14.8 millimetres. And we have an X bar of 15.1 millimetres. So you can see there's a slight difference between our calculated values and those stated in BS4. One of the reasons for that is that the British Standard section will account for the fillet radii shown here and also at the top of the angles. Those are actually curvatures that we do not account for in our analysis. We just have sharp edge rectangles, but in BS4 they will account for fillet radii. Because obviously when the section is extruded, it has these curvatures. So that's why I have a very slight difference in the values. But you can see for all practical purposes our method is reasonably accurate. I want to just take you briefly through question 3 in our workbooks. Here we have a rectangular section shown in the sketch below, but it has a circular hole punched in it. So the rectangular section is 900 millimeters by 1200 millimeters, and we have a 400 millimeter diameter hole punched in the plate, which is a location of 800 millimeters up from the base to its centroid and 300 millimeters from the right hand vertical edge to its centroid. So part A wants us to determine the Y bar location for the centroid, and part B wants to calculate the X bar location. The approach we adopt here is identical to that of all the previous examples and questions we've considering. The only thing that's different is that because we are considering a hole in the plate, then that will be a negative area in our table. So when we work out the area of the circle using pi r squared or pi d squared upon 4, whichever formula you prefer to use, it will be a negative area and therefore it will generate a negative area moment. So all that happens is you must make sure in your table that you have this negative value against the area you calculate, and then that will have a negative value against the first area moment. So when you add up the various elements, you will be actually subtracting the whole from the overall area and area moments. If you think you could attempt that question on your own, then the answers are shown below for the Y bar and the X bar, but I will outline the full solution on the following slide. Okay, so here's the solution to question 3. I'm just going to overview it for you generically. I've labelled element 1 as the plate here and element 2 as the hole. Again, my table includes the yn values and the xn values because I'm working out both the Y bar and the X bar here. Okay, here's a brief overview of the solution for question 3. First of all, we calculate the areas. So area 1 of the rectangle, 900 millimeters multiplied by 1200 millimeters. So 1.08 times 10 to the 6 millimeters squared. Notice though for element number 2, this is the hole. Area 2 has a negative value because we're removing the hole from the section. I've used the formula pi d squared upon 4 here. You may want to use pi r squared. But the area here is negative 125,664 millimeters squared. So when we summate the areas in the bottom row, we have 1.08 multiplied by 10 to the 6 minus the 125,664. So that's where we get the 954,336 millimeters squared total area from. On this slide, I've added in the y dimensions to the centroid of element number 1. That's the rectangle. That will be half of the 1200 millimeters in the vertical position to get to the centroid here. And we can see clearly the centroid of element number 2, the circle, is 800 millimeters from the bottom datum. Considering the x dimensions here, for the element number 1, the x dimension would be half of the 900, so that's my 450 for left-hand datum. And from the geometry given, the overall width of the plate is 900 millimeters. And we're told that the centroid of the circle is 300 millimeters in for the right-hand end, so that will mean the x dimension for element number 2, the circle, will be 600 millimeters. That's shown here. On this slide, I've now worked out my area moment about the horizontal axis. So here we've multiplied the area for each element by its y dimension from the horizontal datum. Again, notice here how the negative area multiplies to give a negative area moment, element number 2, the circle. Similar process to calculate the first area moment about the left-hand vertical axis. This time it's the area, but multiplied by the x value to give the an xn values. Again, notice how we've got a negative an xn value for element number 2, the circle there. So to complete the table, we just summate the an yn column to give the first area moment about the horizontal datum, and we summate the an xn column to get the first area moment about the left-hand vertical datum. The calculations of the y bar and the x bar are exactly as we've done in the previous questions, so I'll let you review these at your leisure. But the y bar works out to be 573.7 millimeters from the bottom datum, and the x bar works out to be 430.2 millimeters, and that's from the left-hand datum. The x and y bar dimensions are shown from the respective datums in the diagram. So there's the full solution for question 3. Question 4 is for you to attempt. You have to work out the centroid location of this L section. Centroid location will be somewhere in this region here. Answers are stated here. The X bar value is 15 millimeters, and that will be measured from the YY datum shown here on the left-hand side of the section. And the Y bar dimension is stated as 20 millimeters, and that will be measured here from the XX datum at the bottom of the section. I've shown you an outline of the table to use to help you generate a solution. And here are questions 5 and 6 for you to attempt at your own pace. Again, the centroid location is stated for each of the questions from the respective datums xx and yy. I'm just going to briefly outline the calculations for the angle of rotation. The rectangle shown below on the left is assumed to have uniform thickness and has a centre of gravity at the intersection of the dashed lines as shown. So there's its centre of gravity here. The rectangle's weight force acts through the centre of gravity, C of G. Assuming this rectangle is now allowed to rotate freely about the top left-hand corner, it will take up the tilted position shown by the right-hand diagram. In other words, it will rotate through some angle, labelled theta in the diagram, shown here, from the horizontal. If we wanted to calculate the angle theta, and we know the x bar and y bar, then tangent of angle theta is the x bar divided by the y bar, and we use the inverse function to find the actual angle theta, so tan to the negative 1 of x bar divided by y bar. So there are questions where you can simply be asked to find the angle of rotation in this particular case, and that's the way you would find it using that formula given. Here's an example based on the rectangle shown on the previous slide. We're given an x bar is 20 millimeters, y bar is 50 millimeters, so therefore the angle theta is calculated from tan to the negative 1 of 20 divided by 50. That evaluates to an angle of 21.8 degrees. So the angle of rotation from the top left-hand corner, angle theta is 21.8 degrees. For further practice, an exercise here suggests to revisit questions 3, 4 and 5 reviewed previously and determine the angle theta, assuming that each shape is free to rotate about the upper left-hand corner. So be careful here, the y-bar dimension that we must use has to be from the top of the section. In most calculations we calculate the y-bar for a shape from the bottom of the section, but for calculating the angle of rotation it must be from the top of the section, so be careful. Answer for question 3, angle theta is tan to negative 1 of 430 millimeters divided by 626 millimeters, and that will be the y-bar from the top of the section. And that evaluates to 34.5 degrees. The answers to question 4 and question 5 are also shown. I'd encourage you to stop the presentation and attempt that exercise. And the final question, question 11. We're given a trapezium section that's shown in a sketch on the right hand side here. And we're asked to calculate the centroid location. So that's to calculate the x bar, shown here from the left hand edge of the section, and also the y bar value, shown here from the base of the section. We're given a hint in the question to split the section into a triangle and a rectangle. If you think you can attempt the question without any further assistance, then please feel free to do so. The answer for the x bar and the y bar is shown in the brackets here, but I will outline the full solution on the following slides. So here's question 11, the full solution. As a hint suggested in the question, the first thing to do is to split the trapezium section into a triangle and a rectangle, because we know the centroid location for the triangle and we know the centroid location for a rectangle. I've labelled the triangle as element 1 and the rectangle as element 2, that's arbitrary labelling, but it just provides ease of reference. Diagrammatically, the centroid for the triangle will be somewhere in this region. It'll be a third the way to the left from the vertical axis and a third the way up the height of the triangle. And we know the centroid of a rectangle is found by bisecting the corners. Question 11 continued. Here's the full tabulated solution for our triangle and our rectangle. Just note for the triangle, to work out the area, it would be a half the base times the height. And when working out the y dimension of the triangle element from the horizontal datum here, remember the formula we were given for a triangle in the early part of the presentation. The centroid of the triangle is a third the way up the height. So to find the y-bar position for the triangle from the datum at the bottom of the trapezium, it will be 35 add a third of the height of the triangle, and the height of the triangle is 15 millimeters. So the y dimension for the triangle from the datum here will be the 35 add a third of 15, and that will give us the 40. As for the x dimension for the triangle, then that will be 2/3 of 100 from the left-hand edge. I'll let you review the rest of that slide at your own pace, as the overall solution is very similar to that we've undertaken previously. Here's the bibliography used to help generate the presentation. And I hope this has been of use to you, and thank you for viewing.